heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world.
All right, good evening, everyone, and welcome to Mount Washington Observatory Science in the Mountains lecture series. My name is Brian Fitzgerald, and I'm the Director of Science and Education here at Mount Washington Observatory. Thanks so much for joining. And here to join us also this evening to help us learn about the environmental challenges facing extra-Earth exploration is the Director of Education at McAuliffe-Shepard Discovery Center in Concord, New Hampshire. Her name is Mirka Zapletal. Thanks so much, everybody, for joining us tonight for the program. If you're not familiar with Mount Washington Observatory already, we are a private nonprofit organization, and our mission is to support advance the understanding of the forces that create Earth's weather and climate. And we accomplish that through a few different realms. One, through our around-the-clock weather observation and forecasting at our Summit Weather Station, through creating educational programs and delivering to a variety of audiences, and by conducting research and product testing services. If you have questions for tonight's speaker and you're joining us through Zoom, please make sure to use the Q&A button. You can find that at the bottom of your Zoom screen tonight. We welcome questions throughout the entirety of the program, and we'll make sure to leave some time at the end. If you're joining us through Facebook, thanks so much for joining us through that realm. We won't be able to join and answer your questions live through the program, but we'll try our best to get to you at the end. So if you'd like to join us through Zoom and ask some questions in the future, you can join over at mountwashington.org/SITM. All righty, well, let's kick things off with a nice poll for everyone who's joined this evening. We have some questions that Mirka was kind enough to, some nice trivia for everyone joining tonight. The first question is actually for me, just curious where you're joining from tonight, perhaps a state within New England. Or perhaps you're joining from outside New England, or maybe even from outside the USA. Curious where you're joining us from tonight. And then we have a few trivia questions. So first off being, how big is the Earth in comparison to the moon? Is it 3, 4, or 5 times the size? Is Earth 3, 4, or 5 times the size of the moon? Next question, what is the most abundant gas in Earth's atmosphere? For those of us who follow along with meteorology and atmospheric science, I expect lots of you to get this one correct, either oxygen, carbon dioxide, or nitrogen. And then lastly, how many degrees is Mars tilted on its axis? 15, 20, or 25 degrees are your choices there. So if you're on Zoom and you can join in through the poll, I encourage you just give me another 10 seconds or so to get your responses in. It looks like quite a few of you have already participated, so thanks. And we'll wrap up in about 3, 2, 1. All right, we will end the poll there and share some results. And it looks like the Granite State wins out here at just almost a third of you joining from New Hampshire. Thanks so much for joining. And we have good representation throughout New England. All of our New England states represented tonight. And then certainly quite a few of you, quarter of us joining tonight are from outside New England. So thanks so much once again for joining. Now on to the trivia. How big is the Earth in comparison to the moon? The vast majority of you thought 5 times the size of the moon. Okay. 68% of you thought nitrogen is the most abundant gas in the atmosphere combined to oxygen or carbon dioxide. And then a little more split here, but actually almost half of you saying 15 degrees. Mars is tilted 15 degrees on its axis. I don't know the answer to that one for sure. So be curious what Mirka has to say tonight. So I'll stop sharing there. And I would love to turn it over, in fact, to Mirka. Mirka, can you hear me okay?
Absolutely. Hi, everyone. Thanks for being here. I'm excited to talk about what it means in terms of places that we want to go for extraterrestrial exploration. So I'm going to be honest that I did have to do some digging to find some of the information that I'm going to be sharing with you tonight. But when Brian and I talked about this, the idea was to kind of think about climate and then take that into an outer space location and think about what climate is like there. So what I'm going to be doing first is I am going to get myself all set to share my screen. So if you'll give me a moment for that. And then I'll start my show. There we go. And so thinking about what it means to have a climate in another place. If you joined me for a previous presentation with the Mount Washington Observatory, we talked more about specific weather examples, events, records, things like that. And so this is a bit of a deeper dive in terms of the conditions that people would, or machinery would experience if we're talking about really getting off of Earth and things like that. So what I chose to do was to look really at a place we've been several times and a place that we talk a lot about getting to. So looking at the moon and Mars, and then kind of thinking about these conditions here and what it means for surviving in a space like this. And I was surprised by some of the stuff that I found out. I was also surprised by some of the stuff I couldn't find easily. I thought it would be a little easier with some of these things. But the idea here is let's imagine this. Let's really think about this. NASA is talking about the Artemis program as the next step to getting humans onto the moon. Certainly we haven't been there in quite some time. And so thinking about getting there and establishing a real presence so that it's more of a permanent thing. And then from there, let's talk about going to Mars as well. And so what we're going to kind of look at here is what the conditions on the surface are like. And we'll talk a little bit about kind of what's going on underneath the surface. But imagining from a human point of view, what are the things that we're paying attention to? And so I wanted to start off with some images that maybe we are at least slightly familiar with when we think about space exploration. In fact, one of these images is from NASA talking about kind of future steps and things like that. The other one, to be perfectly frank, is from the Jetsons. So I've got a pretty good broad look here at what we think about in terms of future habitation and things like that. And we're going to talk about why some of this works and some of this doesn't in terms of what we've seen imagined, what the future might look like when we leave Earth and we live someplace else, or we spend long periods of time someplace else. So this is kind of where we're starting from, and then we're going to go step by step. And I'm going to have us start with the moon. So the moon, is something that we're very familiar with. If you're like me, you're looking at the sky on a regular basis. So it's, an old friend. It's there all the time. And in some ways, it's maybe something that we don't notice as much anymore just because it's a part of our world. But certainly when we get to the moon, things are very different. And so I encourage you, certainly over the next few nights, if you get a chance to find the moon, we are getting closer and closer to the full moon. It's just a few days away now. And so it'll be more and more prominent in the sky, and you can kind of look up and see some of these things that I'm talking about. But first of all, I want us to think about the movement of the moon, which is a little difficult. We're so used to seeing the move in one direction. And what I mean by that is we're used to seeing it move across the sky. We're not thinking necessarily about how the moon is moving around its own axis, how it's spinning on its own, but it does. It's just that it's spinning at the same time that it's moving across the sky, and it's working just perfectly. Its motion is so perfectly matched that we always see the same side. There's always the same part of the moon facing us, even as it spins on its axis and it moves around us. And so for us, that may be very comforting. We always see the same side. It's very familiar to us, that kind of thing. But when it comes to actually being on the moon, there are some huge implications in terms of what this means. So if you think about how we always see the same side of the moon, right? And as the moon goes through its phases, as I'm showing you here in the moon going through its phases, you can see that those phases kind of progress across the surface of the moon. So first we see this part being illuminated, and then we get to first quarter and half of it is illuminated. And then we get to the waxing gibbous and now most of it, and then to the full, and then to the waning, and we work our way back through toward new again. You can see that sunlight shifting. What's actually happening is the moon is going through a day. As you see that whole process of the moon's phases, as it gets, more lit up, and then less and less and less, the moon itself is going through one day. It's 27 days for us, but it's one day for the moon. And so if you think about our days, right, the sun comes up, things get warmer, the sun gets down, goes down, things get cooler. Repeat over and over again. It's the same process. It's just that on the moon, because one day is 27 of our days, it's 324 hours of sunshine, followed by 324 hours of darkness. So it's a very long day. And that really changes things. That's one of the things about the moon that changes what it's like to be there, because the cycle of the moon itself says that a part of the moon is going to be heated up for a very long time, 13 and a half days before it goes into darkness. And then it's going to be cooling down and in the cold for a very long time. And then it will repeat it over again. The other thing that is kind of interesting about the moon is that it just has a slight tilt. It's officially, I believe, 1.54 degrees. But it's just the tiniest little tilt. And that means that there are actually no seasons on the moon. The first day of the year is the same as the last day of the year in terms of the amount of light and things like that. You're not seeing a change that way. So conditions on the moon are really predictable, which is great, but this tilt does definitely change kind of what it means to experience a year on the moon, because the changes really aren't that intense that way. We don't see seasons up there. There are some other things that also make life on the moon pretty intense. But what we want to think about when we're looking at the moon is, first of all, that this is a space that has very long days, no seasons. It's considerably smaller than the Earth. And I have to admit that one of those poll questions was a bit of a trick right there. The moon is about 1/5 the mass of the Earth. Okay, so if we're talking about comparing mass, but if we were talking about maybe diameter, for example, the moon is about 1/3 the diameter of the Earth. So there are a couple of ways to kind of compare size. So that was a bit of a trick question. But oftentimes we talk about it as 1/5 because we're talking about more of a substance versus the width aspect right there. So we're on the moon. There is a very, very long day. There are no seasons. What this means is that you have really, really high temperatures and then you have really, really low temperatures. And granted, it takes you 27 days to cycle through those temperatures, but that's what we're talking about. So this image comes from, most of my images will come from NASA. This one is specifically called the Diviner Lunar Radiometer, which is basically a huge thermometer. It actually uses, I believe, 8 different instruments to figure this all out. But basically, it's a huge thermometer doing readings of the planet as it goes around again and again and again. And then they compile all of this. And this shows you our range between daytime and nighttime. So as you would expect in any kind of temperature reading, red is hotter, blue is colder. And so you can see that on the side that's lit up right here, we're talking about getting up to possibly 260 degrees Fahrenheit, depending on conditions and things like that. And then as you transform into nighttime, we're talking about getting down to negative 280 degrees Fahrenheit. So it's a huge range right there, right? Over 500 degrees difference between your daily high and your daily low. It's just that your day is 27 Earth days long, so it takes you a while to go through those. But we do see some really, really hot and then really, really cold, which made things really challenging actually for the astronauts who went there, because they were on the lit side of the moon when they were there. So they were getting bombarded with heat from the sun. So they actually had a cooling system they had layers of insulation and then both a cooling and a heating system within their suits so that they could have a reasonable temperature while they were dealing with this. And certainly any mission going back to the moon, depending on where they go, might even have to deal with more cold temperatures and things like that. So you're having to deal with not just, you know, boiling hot or freezing cold, it's both. And so how do you plan for those things as you do that? What's interesting is that we do see some places in the moon that don't have as big temperature swings. So this is the same, this is the diviner right here providing data here. And so the red is daytime, or the mostly red is daytime, and the blue, mostly blue, is nighttime. And if you notice, the nighttime temperatures are pretty much just horribly cold. Like that's just what we're dealing with. But the daytime temperatures, we've got a lot of really hot, but if you look right down kind of in the center here, there's a bunch of blue and purple, which is really, really cold. And what we're seeing is actually craters in the poles that are in shadow. And you can really see the shadows here because the lip of the crater is so sharp. So that we do know that there are a few places at the poles where they just never get sunlight, which means that they're just always incredibly freezing temperatures, which is difficult in one way, but we think is a good bet for places that would have frozen water available for any future plans we have in terms of the moon. Water is really heavy. And so bringing up a supply of water takes a lot of energy, takes a lot of fuel to get that off the ground into orbit and then up to the moon. So when we talk about astronauts on the ISS or something like that, their water recycling system is incredibly complex because they are trying to save as much of this heavy commodity, this important and heavy commodity as possible. So if there were water resources, frozen water resources on the moon, now we don't have to bring all of that water with us. This simplifies things as well. So although these parts of the moon are incredibly cold, and I personally wouldn't want to spend any time there, they may have some good resources that we could use. And the reason that they're always in shadow, because you might be thinking, well, but if the moon's on the other, or sun's on the other side, won't there be a nice, you know, sunlight hitting it from the other side? It's true, except that 1.54 degree tilt is just enough. It is not enough of a tilt for seasons, but it's just enough of a tilt that some parts of these craters are always in shadow. And so that's how we have these areas where we think there might be frozen water. Now, to get to that frozen water, we're going to have to deal with some incredibly cold temperatures. On the southern pole, which is what we're looking at right here, we've registered temperatures that are negative 396 degrees Fahrenheit. In the northern pole, we've registered numbers that were negative 413 degrees Fahrenheit. And just to kind of give you a sense of how cold that is in comparison, you know, we're talking about Pluto. Its general range is around 400 degrees below 0 Fahrenheit. So when we're talking about like a place that is 8 hours at the speed of light away from the sun, not really getting any heat at all, it's negative 400 degrees Fahrenheit. And yet when we talk about the northern pole of the moon, we've also got spots that are hitting those kinds of temperatures. So it is incredibly cold in comparison even. In addition to these crazy temperature swings that you deal with, you also deal with some other aspects of the moon or things that are missing. So we know a little bit about the moon's past. I mean, partly because current theories say that it's made of the same stuff as Earth. Something hit the Earth, knocked a big bit of its material off into space that then coalesced into our moon. And we believe that there was a magnetosphere or a magnetic field in the past. The Earth has an incredibly powerful one. Not every planet has a really nice magnetic field, but we've got one, which is fantastic. It protects us from cosmic radiation and solar radiation and things like that because of how those solar particles and other particles interact with our magnetic field, and it kind of channels it. The moon had one, but at some point it stopped. And there are a couple of theories. Was this because of just general cooling in the core? And eventually the dynamo on the inside stopped. Is it because something hit the moon. That's another theory, is that something like hit it and kind of stopped it from moving. So there are a couple of things that we have there. We just know that there's not actually a magnetic field right now. And this, the way that we think of it, our magnetic field is hundreds of times stronger than the moon's. There is a bit of like surface magnetism there, but it's definitely not what you need for protection from radiation. And so that combined with a very thin atmosphere, it is there. I do want to point out there is an atmosphere on the moon, but it's very, very thin. We consider it an exosphere. So there's really no erosion or weathering right now. But this means that there's really nothing to halt or redirect solar and cosmic radiation. And I brought this picture here of the Earth kind of experiencing solar radiation, solar wind. And then you can actually see how our magnetic field is clearing stuff out of the way. I mean, it even leaves like this trail out behind it where you can see this open space that's free of the solar wind, because our magnetic field is so good at channeling those particles. We see the aurora and they're beautiful, but that's also really helpful for us that it's channeling these particles around us. If you look at the moon in this picture, the moon is like this little tiny dot. And it is casting a bit of a shadow in the solar wind because it is absorbing some solar wind, but it doesn't have that same buffer around it. And so it is getting hit with solar radiation all the time, except for a few specific moments. That what can actually happen is that you'll have a solar burst, like a flare, will send an incredible wind, this burst of particles toward the Earth. And what will happen is that this cone you see kind of spreading around the Earth from our magnetic field actually condenses. It becomes much narrower on top and bottom. And sometimes the moon ends up kind of like suddenly in the zone that's not getting the solar wind. It'll suddenly just be out in space without this solar wind because of how everything is being condensed by the pulse. And you might think that's good. It's just that, you know, solar radiation, cosmic background radiation, there's just a ton of radiation. So there's really no shelter for the moon in terms of radiation. And that makes it really difficult. In addition to this, things just hit the moon all the time. In fact, we know that there are periods where tons of things have hit the moon, but there's, once again, no atmosphere to really burn up anything coming toward it. So it's constant impacts and it's constant radiation all the time. Okay, and so I saw some of these questions, so I was just going to hit some of them. Doesn't the moon lose its supply of ice in the process of sublimation? So the answer to that is no. And it's actually surprising how much water is there. You're right that sublimation becomes an issue, but in these areas where there's constant shadow and you're not ever getting that sunlight, you're not going to have enough energy to sublimate. But as it turns out, this was kind of a shock to people. A few years ago, one of the Indian satellites was able to detect traces, like the signature of actual water droplets on the moon, and it seems to be caught up in the soil. It's not in that top layer. There seems to be enough of this dust and these smaller pieces of rock, which are created by all of these impacts, that it seems to kind of lock things in. What we have noticed, though, is that if you breach that top layer and expose what's underneath, then you do actually start losing water to sublimation, because there have been a couple of times where an impact was registered and then they could see the signal of the water evaporating. So it kind of depends on where you are in terms of shadow or sunlight, but it also depends on how pristine, how unbroken that very top layer is there. And then, sorry, moving stuff around so I can see all the questions. Okay. Okay, we're going to talk about the atmosphere in a little bit, so I'm not going to do that one quite yet. Is the diurnal temperature range less near the poles due to lower sun angles? In the sense that if we go back, hold on a second, and is there a Goldilocks zone around one of the poles? It would be a great idea, right? If there was this area that had the Goldilocks zone. But here's what I'm going to do. I'm going to get us back into here and I'm going to go back to our pictures. If you look at this, our picture of this, Here's our pole up at the top. Here's our pole down at the bottom. And if you notice, that red goes all the way from top to bottom. And that blue goes all the way to top to bottom. I would say that if we were looking for a Goldilocks zone, what we'd actually be looking for is some sort of crater that's shaped in such a way. Maybe it's got lots of jagged edges or something like that, so that there's some sun and then it stops, and then there's some sun and then it stops, and then some sun and then it stops, to keep us in more of a middle temperature. The problem is, however, to be honest, that because of that really thin atmosphere, the moon cool. I mean, you can see the moon cools down really quickly. You can see the gradient. It goes from crazy hot to crazy cold over a very short space. And that's because it just loses the heat so quickly. So that looking for that Goldilocks zone is really challenging. So there have been other suggestions. Instead of finding the Goldilocks zone, is there another way that we could do this? Hold on, let me get in here. There we go. So one of the suggestions has, been that instead of having something like this, which would be on the surface, exposed to those huge temperature swings, exposed to all of that radiation, all of those things, is there another option that we have? This is a picture from NASA. This is a drawing from one of NASA's artists, imagining what, could be happening in the future, maybe through the Artemis program on the moon. But we have to be honest that this is a really challenging environment, and this may not be the way to do it. And instead, people have suggested digging down. Obviously the moon's surface could be helpful for some things. I mean, think about the solar panels you could be working with and for energy. But if you're talking about screening people from radiation, and if you're talking about moderating the temperature and not having to deal with those crazy swings, underground may be the way to go. Some have suggested looking for lava tubes, because there is a pretty volcanic past in terms of the moon, looking for something like that, which would allow us to establish a space that is kind of buffered from the environment, and then obviously going up onto the surface from time to time, but not constantly being on the surface, just because of how difficult it is. Now, in comparison, I'm now going to take you to Mars, which has some things that are so similar and some things that are so different, but it feels like almost like a flop. When you compare it to the moon, it's such a different way of thinking about things. So days on Mars are about the same. So if we were talking about experiencing a Martian day, it would be very similar to our own, slightly longer, but that's not really a huge difference. But years are about twice as long, because Mars is 1.5 times farther away from the sun. So it just takes it longer to go around. So the day is the same, but the year is very different. The current tilt is about the same as well, which means that Mars does have seasons, which is pretty exciting. Mars does have, some changing weather and climate, which I'm going to show you as well. And the current tilt is about 25 degrees, but you'll notice that I said there was a huge swing in the past. And this was one of those really fascinating things that I got so into while I was trying to get good images for this presentation, because it is remarkable what has happened. There is a lot of agreement that there have been some huge changes in the tilt of Mars, right? And just for comparison, the Earth's is about 23 degrees. So Mars and the Earth are very similar, but we know that Mars has this gigantic wobble. And when I say gigantic, possibly 60 degrees total, between 0 and 60 degree tilt, possibly, certainly 15 to 35, everybody agrees about that. So what this means for Mars is that if we look at how the tilt has changed over time, at some point, it was pretty close to up and down, similar to the moon. Then at some point, it had actually made it past 45 degrees and then come back up again, and it goes back and forth. It does this whole process, this cycle of wobbling back and forth. And that changes the climate on different parts of Mars continuously. And when I say continuously, this is a really long process. This is not 100 years or something like that. This is 10 to 20 million years. But it's still this continuous cycle of change. And it kind of looks like this as it's going around. So you can kind of see the swinging back and forth of the tilt as it makes its way around the sun over and over and over and over again over, millions of years as it repeats this cycle. It does this whole thing. We think this is because Mars has 2 small moons instead of one bigger moon. So our moon is instrumental to our lives in a number of ways. In addition to being a nice light in the night sky, it influences our tides, but it also stabilizes our tilt so that we don't wobble so much. Because if you think about the solar system, there are a lot of big things in our solar system. We're orbiting the biggest one, right? The sun is the biggest, and it is most of the stuff in our solar system. 99.8% of the stuff in our solar system is in the sun. But there are some other big things too, and all of those gravities are pulling on us. So if we're kind of off on one side, if we're tilted, we can get pulled back and forth regularly. But the feeling is that our moon, because it is something with a bunch of mass close to us, stabilizes our tilt so that we really don't wobble that much. Mars, on the other hand, has 2 small moons that we think were asteroids. So they're not particularly big. One of them, I believe, is 2 miles across. And so they're just not enough mass, not enough stuff to stabilize the Mars orbit. And so instead, it does this like more of a tilt, less of a tilt, more of a tilt, less of a tilt. And over this long 10 to 20 million year cycle, what that means is that the parts of Mars that are frozen change completely. So if we look at the picture on the right, just kind of walk us through this, the very bottom Mars, the very bottom globe right there, which has a lot of white at the top and a lot of white at the bottom, although I pointed to the bottom first, but that's okay. This is less of a tilt. So we're seeing more polar ice caps, right? It's cold up in the northern pole, it's cold down in the southern pole, and then it's more of a tropical-ish, if that's what you can call it for Mars, environment along the equator. Now, as that tilt starts to change, and so going up to the upper left-hand globe right here, as that tilt starts to change more, now the parts that had the ice, the poles, are not as cold as they were before. So that ice starts to melt, or in the case of Mars, more of sublimation. But other parts of the planet start to get colder. So we start to see some redistribution of where the ice is. And as the tilt hits kind of its maximum, now we've got ice ending up near the equator, and we've got much warmer temperatures happening near the poles. And so we see this kind of switching back and forth. And in fact, some scientists feel that seeing how the Martian climate has changed like this over time is really helpful for us in kind of understanding how things can be changed so quickly and redistributed so quickly given climate change. But so for Mars, it's fascinating because it is such a huge change in the conditions. And so what we know is that there used to be ice in one place, but then later on there was ice in a totally different place and then ice in another place. And so it keeps like moving things around, which is why if you think about the surface of Mars, there are just examples of huge rivers, all sorts of channels being cut by water, also areas where we know there were deltas or things like that. And so all of that water is moving because of all of these changes happening. What's crazy, another crazy level about Mars is that in addition to this huge wobble, there's actually a tiny little wobble that's happening just a little bit, like a degree or two. But once again, it's enough to make some differences. So this is a cross section of the northern polar ice cap. And I want to point out that on Mars, the polar ice caps are water and carbon dioxide, not just water. Okay, so frozen water and frozen carbon dioxide. And in fact, most snow on Mars is carbon dioxide when we see it. If you look at this cross section going through the ice cap, you can see that there are these lines, like it's these nice layers. And what you're actually seeing are layers of alternating ice growth and then dust deposited on top of that, and then ice growth and then dust deposited on top of that. And these are representing smaller changes in the Martian climate that are about 104 to 107 year cycle of that little wobble just being enough to change some conditions to melt a bit more ice this time and then tilting back the other way. And now we're building a little more ice this time, and that kind of a thing. So it almost is kind of helping us see this smaller cycle, this little tiny part of the wobble versus the bigger one right here. But in any case, what we've got is that water and ice have just been, and carbon dioxide have just been redistributed multiple times in the past. And so that creates some really interesting conditions on Mars. But this tilt, you know, depending on how that tilt is kind of angled, means that we do end up with seasons, at least for us, that are quite familiar. You know, Mars goes through a southern winter with a northern summer, a southern spring with a northern fall, a southern summer and northern winter, and then southern fall and northern spring. So very similar to us. It's just that these seasons last twice as long because Mars' year is twice as long. So it's a longer journey around the sun, takes more time to get through those seasons, but those seasons would be very familiar to us just because of how that tilt, you know, manifests this right now. And what we find is that we could even almost create some zones, whereas the moon is just like hot and cold alternating. On Mars, we actually do see like a seasonal frost line. We see these warmer areas here along the equator going right across the orange. Then we have kind of the less temperate going up to our seasonal frost line. Then the colder, and then the blue at the very top, that's where our ice caps are. So we can see that there are these zones of temperature experience on Mars, which we don't see on the moon. And in many ways, it really is that tilt that's making that happen. But there are a couple other factors here as well. And I'm going to come back to this map several times just because it's a great way of looking at Mars, but we're also going to look at some weather reports from specific locations on Mars to give us a better sense of what it's like. So Mars tilt creates some interesting situations in terms of what different places are experiencing. And so this is a great graph that talks about Gale Crater, and Gale Crater is where Curiosity is. So if any of you are familiar with the rover Curiosity, who has been there since 2012 and is still going strong after what was expected to be a 9-month or so assignment. Curiosity has been doing phenomenal stuff and recording temperatures and weather regularly. And so what NASA did was to put together this chart, which shows you Gale Crater compared with Los Angeles. And I know that we're not in Los Angeles, but I felt like this was such a great visual because it is a place that we're familiar with. And the other thing that it does is it shows just how much those temperatures change there. So if you look at the range of like the high and the low temperature on Gale Crater, and then you compare that to the high and low temperature range in Los Angeles, on Mars, we do have these really, really big swings. When we look at that, it just kind of gives us a sense that, first of all, LA has got a warmer temperature, but LA also has this smaller range of temperatures. Whereas in Gale Crater, it's cooler, but it also gets very cold there. So the question is the center of Mars hot or is it completely cooled? It is not completely cooled. It is hot. And our feeling is that, yes, there must have been some time and I'm going to show you some examples where there was absolute mountain building, some amazing stuff happening. But we know that things have changed quite a bit on the surface of Mars. And we've got some ideas about how that happened. But certainly if you were to cut Mars across, like you took the ball and you cut it down the middle so you could see into the layers inside. One of the things that's interesting about Mars, if you compare it to the Earth, or if you even compare it to Mercury, one of the things that's interesting about Mercury, Earth has a pretty good sized core. And it's got a hard core and a molten core, but because it's got a pretty good sized hard core and molten core, there's a huge amount of movement, basically like a dynamo. It's moving and moving and moving. That's part of what creates the magnetic field for us. And then we've got our other layers as well coming up from that. If you look at Mars, it still has the core, it has the mantle, it has the crust, but the core is much smaller in comparison to the entire planet than Earth's core is to ours. And so there is heat in there, but what it means is that there was certainly more rapid cooling happening in Mars than happened on Earth, or is still happening on Earth. So it's not completely cooled, but it doesn't have the same system going that Earth does, so that that reservoir of heat isn't as perpetual there. I know that it's not totally perpetual, but when you consider that the Earth is, you know, billions of years old and still going, it's a pretty good dynamo that we have there. So on the surface, what we've got, and there's some really interesting things about temperature on the surface that I'm going to talk about as well, but Gale Crater has this huge range. But I do want you to notice, it says spring, summer, autumn, winter. So you can see there's the seasonal change happening here, right? It's warmer in the spring and summer, cooler in the autumn and winter, which we would expect. Just kind of keep that one in mind. And I'm going to show you some recent readings. This is from 2 weeks ago. Readings on Mars in Gale Crater from Curiosity. You'll notice that the maximum temperature was not particularly warm. It's definitely cold there right now. And the minimum temperature was really, really, really cold. So we're not dealing with summertime at the moment. The other thing that's really interesting, I think, personally, is if you notice the sunrise sunset information, it's really consistent. I mean, it is changing, but it's barely changing. We don't quite have that same consistency when we see some of our changes from day to day. So the idea that you could have 5 days in a row where the sun is coming up during the same minute, we wouldn't have that. So we see that there's a bit less. Remember, their year is twice as long, so it takes them longer to go through all of those stages. So it is fascinating to me to kind of see this. But you can see it's not warm, right? I mean, that maximum temperature is something that we could be familiar with in the winter. We have days where it's, you know, a high of 10 or something like that, but that minimum temperature is certainly not something that we're used to dealing with right there. How do we know what the cross-sectional consistency, like the mantle, the core, et cetera, is? To be honest, a lot of it is remote sensing. It's sending waves and then looking for signals. And so also looking at how certain things behave. So we know, for example, that Mars does not really have a magnetic field. It might have in the past, but it doesn't now. So that tells us to begin with that there's not a lot of motion happening in the center. And then if we look at how waves from different events are kind of transmitted through, you know, when we have an earthquake here on Earth, we can actually look at the movement of those waves. And when we get a reading somewhere else, when those waves make it to the surface, we can use that information to figure out what those waves were traveling through. And then we can do other things. So it is remote sensing. And some of it is kind of deducing, well, if this is how it behaved, then that must mean that this is here. And then we use what we know about the Earth as well to kind of figure out how things are working in other places. So it's a combination of things. Obviously, we never get to actually see it, but we try to use as much information as possible from different sources to make a model that makes sense. That's kind of how it works. Now, Gale Crater is actually almost on the equator. So this blue, we're back to our global climate zones, this blue circle right here, that kind of like little round horseshoe in this line right there, that's Gale Crater. So that's where Curiosity is right now. And you'll notice it is about the equator. So those temperatures, that high and that low, there's some seasonal difference happening here, but it's not a huge amount of seasonal difference as we go through that. What's interesting though, is that you do get to see the spring, summer, winter changes. I wanna compare that with a different location. So Curiosity is one of our rovers. It's been there, as I said, for quite some time. And we have other robots that are working there too. Most recently, Perseverance was sent as a rover and is working to look specifically for signs of life. But we also sent a robot several years ago called InSight. And InSight is not a rover. InSight is designed to be in one spot and then start digging down into the surface. So once it got to where it was, which was in Elysium Planitia, that's where it's staying. And it's collecting information on soil, temperature, all sorts of things. It does send back a weather report. So I went and I said, what can InSight tell me about the weather? And this is phenomenal because this is, over a year of weather here. on Mars. But here's what I want you to notice. Okay, so we've got pressure, wind speed, and it's divided up into seasons once again, winter, spring, summer. This top one is temperature. And that line, if you notice, I mean, there's a little bit of undulation. It is not changing very much. That is just a very cold place. Probably it's because it's in a crater, there are some structures that are blocking a lot of sunlight. So it's just simply not getting a lot of sunlight in general, but that is a very cold place. And it's also very consistent, which is fascinating because if you look at the air pressure is changing. The wind direction is changing, things like that. And the opacity, which is down at the bottom, which is basically how much dust is in the air, is changing. But that temperature is just kind of humming along. I'll get to, that's a good question about Olympus Mons. I don't actually have a fantastic answer for that, except for cold, like really cold. But I don't know I'll have to find that one out. I'll see if I can find out what the temperature range of Olympus Mons is. We'll talk about Olympus Mons in a little bit for those of you who are unfamiliar with it. So anyway, so this is coming from where InSight is, which is Elysium Planitia. And what I find really interesting about this information is that Elysium Planitia is actually not that far away from Gale Crater. It's pretty close. Here's Gale Crater, here's Elysium Planitia. It's not that far away. So it's something about the formation of where that is that's changing things so that we don't see that temperature swing. Instead, temperature is a lot more constant. We have, Mars is amazing. I mean, the moon is amazing too, for the number of things that we have going around it. Both the moon and Mars have multiple satellites whose sole job is to collect information on the planet or the moon below it. So when we look at Mars, at the moment, there are, if we count InSight the helicopter, not InSight the helicopter, sorry. And right, I'm mixing up all of my robots now. We have InSight, which is stationary. We have Curiosity, which is a rover. We have Perseverance, which is a rover, and then Perseverance brought with it the helicopter. So if we count the helicopter, there are 4 active robots on the surface of Mars. Plus previously, we had Opportunity, Spirit, Sojourner, Pathfinder, so multiple rovers that were exploring the space and then their batteries ran out or their solar panels got covered with dust or something like that. Then there are all sorts of missions that are satellites simply circling. So yes, there are constantly satellites going around the surface of Mars to gather information. And some of them are very specific, looking for mapping elevation, for example, or specifically looking at temperature. Other are doing things like trying to get a better sense of the atmosphere, trying to get a better sense of changes in gravitational forces as they're moving around, things like that. So it's the same thing with the moon. There are multiple satellites going around the moon. Some are very specific in what they're looking for. Others are kind of generally taking in a whole bunch of information at the same time. So the temperatures on Mars, you know, so far as we've seen, not particularly warm. And the global average is about -80 Fahrenheit. So that's a bit intense right there. But what's also really interesting about Mars is it has a very thin atmosphere, and that means that the temperature at your feet is probably going to be, when you're standing on the surface, is going to be 15 to 20 degrees warmer than the temperature at your head, because that's how thin the Martian atmosphere is, and that's how much the heat is dissipated as you go up from the surface of Mars. And that to me is a fascinating idea, that you would need like to dress for different weather for your head than for your feet, simply because of how the planet heats and then cools. So let me move on to my next slide just so that I get there. So high temperatures, you know, can reach near 70 degrees near the equator. And we do have some readings up to 95 degrees in some places during the height of summer. Low temperatures are really cold, so -220, but we have a couple readings that suggest they could maybe even get to -225 in some specific places. Now, like the Earth, Mars has an elliptical orbit, which means that the orbit is not kind of like a really nice circle around the sun. It's more of an oval around the sun, so that for part of the year, the Earth is closer, and part of the year, the Earth is further away. And for us, what that means is that we in the Northern Hemisphere, we have our summer when we're a bit further away from the sun, versus the Southern Hemisphere is a bit closer when they have their summer. So summers in the Southern Hemisphere are warmer than summers for us. And it's the same thing on Mars, but like taken to a bit of their orbit is even more elliptical, so taken to a bit of an extreme here. So what I'm going to do next is I'm going to play this amazing simulation. This is daytime temperature on Mars over 5 Earth years, which is phenomenal. But what I want you to do is just pay attention to how the colors are moving around. So let's see what I can do here. I can get it started. So hopefully you're seeing that change. And once again, red is hotter, right? Blue is colder. And you can see the swing between summertime in the south and summertime in the north. And that white, that's ice caps right there. And I find the simulation amazing. I'm actually going to play it for you again because I find it so phenomenal for a number of reasons. First of all, notice how red it gets in the southern part, right? Versus the northern summer is not nearly as warm as the southern summer. And that's because Mars orbit is even more of an oval than ours. But there's another moment in this, which I found amazing. And I may have talked through it already. There we go. You see a sudden blip, as if things have suddenly cooled down everywhere. And that has to do with the Martian weather. So Mars has a really thin atmosphere, as I said. You're standing on Mars, your feet are like 15 to 20 degrees warmer than your head. The atmosphere is mostly carbon dioxide. It's actually 95% carbon dioxide in comparison to Earth's atmosphere, where we're talking about, more than 3/4 of it is nitrogen. And then oxygen is our next one. Carbon dioxide is a trace for us. It's 0.0038, I think, or 0.38% on Earth, versus Mars, where it's actually carbon dioxide is 95% of the atmosphere. It's still a very thin atmosphere, but we think it used to be thicker. But because Mars also doesn't have a magnetic field, we believe that it got stripped away by the solar wind over time. And that's part of what led to the drying out of the planet there. But we do see some really interesting weather in terms of dust. So there are these amazing dust storms. This is an example of like a dust devil, this picture right here, which will develop. But Mars also has huge dust storms that will cover the entire planet. And they're more common in the spring and summer. They're also more common, the more of a tilt Mars has, the bigger and more impressive their dust storms are. So there's something going on there. And we think that what's happening a little bit is that as the dust starts moving, now it's kind of capturing the radiation, the solar radiation coming from the sun. So it's heating itself up. And so now that part of the air, the atmosphere has now gotten even warmer. So it has more motion. And then that brings up more dust, which heats up even more. So now we have even more motion. And so we think that's how this happens, that it's like kind of like perpetuating itself by warming more air, and now more dust is pulled up, and now it warms more air. And so that's how you get these huge dust storms that will cover an entire planet. And we know these happen on a regular basis, but there seem to be some trends there. The problem is that because we have a thin atmosphere, just like with the moon, there is exposure to radiation on Mars. And I just want to say, I searched so hard for a radiation map for the moon, and I could not find one. It was so much easier to find information on Mars and images on Mars for this. And I don't know if this is just that it's an attitude of, well, we've been to Mars, so it's been to the moon, so Mars is the next, we should be paying attention, or if it's just that maybe everybody takes for granted we know this stuff about the moon. But it was much easier to actually find some of these things for Mars. So I've got our cosmic ray environment, radiation measurements, because we once again don't have a very thick atmosphere, and we don't have a magnetic field. Once again, we think that there may have been one there originally, but as the planet kind of cooled, it doesn't seem to have the dynamo that we have. Someone asked about the velocities of these storms. And yeah, so what we can say is, you know, on a regular basis, winds on Mars hit about 60 miles per hour. So certainly much less than anything that we see when we have tornadoes and dust storms and things like that. There can be times when they're getting a bit stronger, but typically not beyond 80 miles per hour when these storms happen. So, and that's because of that thin atmosphere. So they're big storms, but there's just not enough atmosphere to like really get stuff moving very quickly. And that, you know, is an interesting thing for us because it does show the value or the challenge of an atmosphere. It allows you to get bigger storms, but it allows you to do other stuff too. Now, just to give you a sense of the radiation, and I wish I had a map for the moon. This is REMS per year, but REMS are typically seen as the same as RADs. So if you're used to hearing about RADs of radiation, it's the same numbers. And you'll notice that Mars surface gets hit with a lot of stuff, anywhere from 10 to 20, and even some places that are above that. Those higher elevation places are even above that. And you might think, well, what does that even mean, really? So I did a little bit of digging. NASA considers that if you are someone working on Earth, so not up in the space station, but if you're someone working on Earth and you are exposed to 5 REMs of radiation per year, that should be your maximum. And the average person, just to give you a sense, is exposed to more like 0.6 REMs per year. So when we say 10 to 20, that is a huge amount of radiation. That's many times more than the average radiation that we would experience here on Earth. And so that's why the radiation issue is a problem. It's not just that there's a heightened level of radiation, it's just that it's a really high level of radiation. And then if you look, there's the cosmic ray environment, but then if you look at this graph over here, which is showing your dose rate like per day, you'll notice that there's this huge spike. So everything kind of happening below is this background level of solar wind and cosmic radiation. So that's kind of what we're already dealing with. But if you have that solar flare, if you have that solar pulse, what we sometimes call a coronal mass ejection, you can see those numbers go up dramatically. And once again, without a magnetic field to shield you, without an atmosphere to shield you, or at least a very thin atmosphere to shield you, you really are much more exposed than we are here on Earth. And that's why people talk again and again about what about underground? Because there are ways to shield you from radiation, but there are things like you build stuff out of lead, which isn't a great idea. And just in terms of weight, getting it there, or you know, water can be helpful, but once again, that's incredibly heavy. That's an important resource. Are you going to use that water to shield you, or are you going to use that water for something else, like helping irrigate food or something like that? So you know, thinking about the radiation is a bit of a downer, but it is really important to think about. Okay, so and I know there are some questions and I'm going to get to all of them, but I do want to show this other just crazy thing before I do this. So I didn't know this. This was something I learned. It turns out that there are electric currents in the atmosphere on Mars. And I had no idea about this until I went searching for my map of radiation and just trying to see the solar wind going around Mars. And it turns out that because there is no magnetic field, that solar wind is kind of like just drifting into the planet. And that's what these like stringy kind of aqua, these are the solar particles right there. If you notice, there are some blue arrows and there are some red arrows, and then we've got our planet in the center. What's happening is that as the solar particles are coming in contact with the planet and kind of the wind is being deflected in different ways, there's actually enough of a charge in that you start to get electrons flowing. So they can measure electric currents in the atmosphere around Mars, which is, it just blew my mind. So I threw that in there because it's just unusual. We have lightning, but we don't have solar wind generating current around us. And I found that absolutely fascinating. But anyway, I just wanted to share that. Now, Olympus Mons, which was mentioned before. I don't know what the temperature range is on Olympus Mons. My guess is going to be that because it is so tall, it is incredibly cold at the top. It's probably just incredibly cold all the time. That thin atmosphere is not really going to hold in any heat from the sun. So it is probably just below zero all the time. It's like going to the top. I mean, I know it's not quite the same, but going to the top of Mount Washington in the summer, it's still going to be cooler up there, even though we're getting a lot of sunshine. Olympus Mons is even bigger than Mount Washington. Olympus Mons is the biggest mountain in the solar system. It is, I've seen different estimates. They all get very close to 70,000 feet tall. And this is kind of what you're seeing. What's fascinating to me as well about Olympus Mons, and it's really shown in this false color picture right here, you can kind of see how big the base is, but you can also see the curve of the planet. Because Mars is about half the size of the Earth, and Olympus Mons is so tall, if you were standing at the base of Olympus Mons, you wouldn't actually be able to see the summit because the summit would be curving away from you. And that kind of blows my mind as well, right there. But just to kind of throw out that, like, this is some of the stuff that anyone going there would have to deal with. Mars does have the biggest mountain in the solar system that we know of. It has a huge canyon called Valles Marineris, and it is so big that it would actually stretch from the west coast to the east coast of the United States. So there are just huge features there as well that would kind of be something that we're dealing with here. So I then asked myself, are there any places on Earth that seem similar? And the ultimate answer is no. I mean, what I've just described to you, especially those extremes of cold and dry, we don't really have that. But if you're looking for some places that start to get us close, traditionally NASA has looked at a number of locations as places where astronauts train because they have some combination of characteristics that make it similar to either the moon or, as we're going forward, thinking about Mars. And so I've got pictures here of 3 of those places. So starting over on the left, Death Valley, because you do get those swings in temperature, the really hot and then the really cold, depending on the time of year. And you've got such a dry space. Death Valley has been used for astronaut training, especially when we think about how hot it can get on the moon, not so much Mars, but on the moon. You know, being able to test out those suits and make sure that they are cooling and maybe they do protect astronauts when you hit really high temperatures. That's part of what was done here. The middle picture is a lava field in Iceland. Iceland has been used for training as well, just because it has regular lava flows. It's so volcanically active that there are whole parts of the interior where you really don't have plants. You really don't have kind of stable structures underneath because there's constant lava over lava, and then it's starting to weather and stuff like that. So it has been used for training there as well, especially for just kind of getting used to the environment and learning how to move in an environment like that, where you've got a lot of loose rock and things like that. And then the picture over on the right, that's the Atacama Desert in Chile, which is the driest desert. It does get incredibly cold there, and what you're actually seeing, these are ice formations right there, where you really do have that sublimation and then back to ice again. There's really not a lot of liquid happening in this space. So the Atacama Desert is another place where we kind of see similarities, but the reality is that none of these are exactly like what we've got up there. Where we're going when we talk about going to the moon and Mars are just such different places. Okay, so now I want to get to some of the questions that I didn't really hit. So thinking about, right, that CO2 is a major component of our atmosphere, right? It isn't. It's something that isn't a huge part of our atmosphere, but that's not the same thing as not having a huge change in its concentration. So it's kind of one of those things where if I have an ocean of water and I put another drop of water into it, I don't see a huge change. But if I have a half a teaspoon of water and I put another drop into it, it makes a difference for that half teaspoon right there. And it's kind of the same thing with carbon dioxide. Carbon dioxide is not a huge part of our atmosphere, but increases in carbon dioxide are large in proportion because it's starting off as not a huge part of our atmosphere. And so there's that aspect of the carbon dioxide thing. But at the same time, I mean, it's absolutely not the same as being 95% carbon dioxide, which is what we've got on Mars. That said, you know, carbon dioxide and some other gases in our atmosphere have greater influence than we might expect from that 0.038%. So we also have to think about it that way. Just because it's a small part doesn't make it an insignificant part. Now, can the public tap into the information of these objects? NASA is required, because its funding comes from the public, it is your information, which means it does take a little bit of tracking down things, because you have to know what you're looking for. And what I mean by that is I have to know, for example, with the moon, that if I want temperature, I should probably be looking at diviner data. Or if I wanted to know more about elevation, I might want to look at the Lunar Reconnaissance Orbiter or something like. You have to have a bit of a clue what you're looking for, and then you kind of have to go on a dive to find it. But that information is all public information, at least if it's coming through NASA, because it is our money paying for it. And so therefore it is all of our information, which is one of the reasons that I love NASA pictures too, because those are our pictures. We fund this. This is for us, and therefore we absolutely can have access to it. European Space Agency is very similar because it is publicly funded, but some others, depending on what country is funding it, may not be as accessible, but certainly with NASA, you should be able to find that, but you may find that you have to ask the question specifically, like what type of information do you want to know about Mars? And then that helps you find the data. Now, this question about Mars having clues to our potential change in climate, that is the question. That's one of the reasons that scientists are so interested in some of these big swings, this 10 to 20 million year swings, and then even these smaller 104 to 107 year wobbles, because Mars shows us what happens when you have a massive repositioning of ice. It also suggests to us, because we see these huge channels, what happens when the ice melts pretty quickly. So it does provide us with some information. It's obviously not exactly the same because our atmosphere is much thicker. We don't lose liquid water in the way that Mars does, but it does certainly give us some information about how an environment can be changed dramatically when you start to heat it up. And so at least parts of it up. And so, yeah, we are curious about what that means. Okay. And with that, I think I got to the end of the questions, and that is also my last slide. So what I'm going to do is I'm going to stop the share. There. Now I went a little bit over, but I had some cool stuff. So I hope everyone forgives me.
Thank you so much, Mirka. I really appreciate that. Yeah, there's some great questions along the way, and certainly would encourage folks now, any lingering questions from along the program here. I know we've collected quite a few, but if folks have questions and you're joining us through Zoom, use the Q&A button that's just down at the bottom of your screen there. And even on Facebook, we'll see, maybe we can pull over a few questions from there as well. Though a little logistically, a little more difficult, but we'll see if we can get some more folks to participate as well. One of the questions I had, actually, just to kick things off, because in fact, I was just reading about it today, the Webb telescope that'll be launching very soon. That is the great hope of many astronomers, both professional and amateur.
Yes.
What is that going to give us any insights for Mars or anything within our solar system, or is
not
that
directly?
Extra?
No, I mean, it's certainly, so Webb is designed to look farther into the past than anything that we've made before, which is why it's being launched, why it has to be launched first of all, and then why it's so complicated that it's like all these crazy folding mirrors that end up and they fit inside and then they have to unfold, because it's designed to look for those really faint signals coming from much earlier in the universe history. So it's not necessarily going to illuminate Mars specifically, but what we're hoping is that it helps us understand how that early universe started to take shape, which would include not just stars forming, but then how the rest of the material around those stars is starting to accrete into planets and things like that, so that we can understand a bit more, hopefully, about how our unique or normal and common our system is, and then how things can kind of change over time. So Webb is much more about the early history of the universe, whereas there are other instruments that we use that tell us a bit more about our solar system and things like that. So that there are some orbiters around Venus. There's another one that's supposed to be launched within the next year or two. Then we've got the stuff that we sent to Jupiter, we sent to Saturn, going around the sun as well. So those are a bit more about specific cases, whereas Webb is kind of asking the bigger question of, okay, so the universe started, then what happened?
Well, so to bring it back to what you were covering between the moon and Mars, I mean, I know you've covered at least a little bit of it, but what are the next steps that NASA and other groups are looking at in terms of potentially being on the moon? What are those sort of next steps and the eventual, I guess, like launching pad ideas from there?
So certainly the most concrete step that we have is the Artemis program, with the idea that sometime in the next, really they were suggesting to us 6 months, it might be 8, we'll see. They're going to start testing the stages for the Artemis unmanned, but just to make sure that these things are working as expected. And the idea behind the Artemis program is that it's not what we saw with Apollo, which was we're going to send a rocket up, it'll get there, it'll come back again. Instead, the idea is let's have a station. We already have a space station, so this will be a different space station, but let's have something that's actually around the moon, so that becomes more of our center for operations. And then we're going from that to the moon, because that means that now we have a permanent presence there and we can do stuff in space around the moon, and then we can also get to the moon's surface. So it's looking much more at a longer term. Let's set up something similar to the ISS, but set it up around the moon. And then let's even see that as a way for us to then launch toward Mars. So I think, we know a bit more about the next 4 years, which is when they're talking about sending people back to the moon. But, on a regular basis, they're talking about the 2030s as, okay, so then we start moving toward Mars as well.
That makes a lot of sense. We have the International Space Station, something that we know functions adequately well in rotation there. So I guess that does make a lot of sense to me. But I mean, in thinking how long it took to put together the ISS into more or less what it is today, how long do you think it would take to put something like that together? It is,
and so it's one of those things where they're kind of working on all that. They call it the Orion Gateway, is what they call it. And so they already have that part started as they're testing the things for actually getting people up into space. So once again, they're talking about that it probably wouldn't be finished by the time the first Artemis mission makes it onto the moon. They'll probably still be finishing up the Orion Gateway, but it will be started and in process by the time that first mission from Artemis makes it to the moon. So they're saying by 2024, there should at least be part of the gateway constructed.
Wow, well, it's always refreshing to think in these timescales. I mean, that seems pretty near term compared to, I guess, the generations of planning, I guess, that are probably happening to go beyond the Earth here.
I have so much trouble kind of comprehending what that process is like, because I always think about New Horizons as my example. So New Horizons was the unmanned probe that did the amazing flyby of Pluto in 2015, and then kept going. It's still going and still sending us amazing stuff. But that was launched in 2006, and it didn't get to Pluto until 2015. And I cannot imagine, my life does not work on that kind of time scale. Like I'm okay with delayed gratification, but 9 years of waiting to see if we could do the flyby of Pluto is too much for me. I mean, this is really long-term planning. And I admire people who are so willing to spend that time working out those little details to make it happen, knowing full well that it will be years before their part actually gets its chance to shine. So.
Yeah, and there are obviously lots of things that can go wrong along the way. This is some cutting edge science that obviously is being engaged with. So there are many unknowns along the way. Well, exciting stuff. I really, really appreciate you, Mirka, putting this together for us this evening. I know I thoroughly enjoyed it, and I know our audience did as well. I want to thank everyone who joined us this evening once again to hear Mirka speak and to continue supporting the Science of the Mountain series. If you enjoyed tonight's free program, we would strongly encourage you to make a donation to help support programs like these over at mountwashington.org. You can hit the donate button while you're there. We are in the midst of our year-end fundraising campaign, so I'd ask that you consider adding Mount Washington Observatory to your year-end giving. If you have thoughts about tonight's program or suggestions for future ones, we'd love it if you take some time to fill out the survey that will follow this program, and also in the thank you email as well from Zoom. And don't forget to join us next month for our next Science in the Mountains program on January 18th. We'll be joined by Appalachian State University Professor Baker Perry, and he's going to take us on an adventure to Mount Everest and talk about his team's expedition back in 2019 that culminated in designing, installing, and now collecting data from the highest weather stations in the world. So don't forget to register for that program. You can watch some past programs as well over at mountwashington.org/SITM. All righty, well, thanks again, Mirka. Have a wonderful evening. Take care, and we'll talk soon.
Absolutely. Good night, everyone.
Night, everybody. Take care. Bye.